Hello, this is the 15th episode of Delving into Academics. For those who don't know, it's where various researchers from biology, chemistry and physics are all interviewed about what they're currently working on and their lives as academics. For this episode, Professor Ken Rice was interviewed about his research into computational astrophysics, particularly focusing on planetary systems. So I hope you enjoy this week's episode. Hello, so I am with Professor Ken Rice today, and he's a professor of computational astrophysics. He started out doing a Bachelor's of Science at the University of Natal. He then carried on to do a PhD there as well, with his dissertation title being a ray tracing study of VLF phenomena. He finished there at 1998 and then went on to become a postdoctorate fellow at the University of Natal, and then on to Bartell Research Institute at the University of Delaware to also be a fellow there. He was then a research associate at the Bartell Research Institute and then went on to become a postdoctorate research associate of the University of St. Andrews and then a fellow there as well. He then did a year as an assistant professor at the Institute of Geophysics and Planetary Physics at the University of California. And then he came to the University of Edinburgh, where he was a lecturer, then a reader, and he is now a professor there. Yep. Thank you for coming on the podcast.
Thank you for having me.
Yeah, so why don't we get started with what you're researching currently?
So currently I'm mainly focusing on sort of understanding planets around other stars, so exoplanets or extrasolar planets. So I do a combination of sort of theoretical work, trying to understand a little bit about sort of how they form, maybe more interested in what happens when stars are very young, so really just after they're formed, and how do processes that operate when they're very young maybe influence the formation of planets, because we sort of know that a lot of the planet building has to happen very quickly, otherwise the planets wouldn't form in time. So big gas giants like Jupiter, they must be pretty much ready to attract all the gas within a few million years, because that's how long the gas around a sun-like star will last before it gets dispersed or accreted onto the star. And so lots of things must be happening when the star is very young. So I do some of that sort of work, which is mainly sort of computational modeling or theoretical work. But I've also got quite heavily involved in actually trying to sort of either find or characterize planets around other stars. So we're part of a team who can measure the reflex motion of a star as it's perturbed by an orbiting planet, and you can use that to then say something about the mass of the planet and its period and how far it is from the star. And if you also have those planets transit in front of the star, so they block some starlight, if they do that, they don't always do that, then you get a radius and you have a mass, you can get a density, you can say something about internal composition. So I'm involved in that as well. So a bit of sort of actually trying to find and characterize planets, but also trying to do some theoretical work on, how do they form, or what processes when stars are very young influence the building blocks of planets.
Yeah, that sounds absolutely amazing and so interesting. And so when you're looking at other planetary systems, what kind of things are you looking for when you're doing studies, say, on the formation of young stars?
So from that side of things, youngsters, so one of the things we think, the Milky Way is a spiral galaxy, and so it has, if you look at it, well, we can't see the Milky Way, but you look at a galaxy similar to the Milky Way, you see those spiral arms. And we think that's an instability. That's because the disk of the galaxy is massive enough to almost want to try to collapse in on itself, but because it's orbiting around the galaxy, it throws the material back out into these spirals. And we think that the same kind of physics probably operates in the disks around very young stars. The disk's massive compared to the mass of the central protostar, and it can start to sort of start up this gravitational instability, and can, we think, produce these spiral density waves. And they can play a big role in trying to move mass through the disk onto the star. So they may play a big role in actually building the star. But if it becomes very unstable, the spiral waves can actually clump into maybe form planets themselves directly. Now we think that doesn't happen very often. Maybe some of the very big planets that are quite far from their stars, maybe they form that way. But we do wonder if maybe those spiral waves might actually help to collect the dust grains and the planet building material and help to at least build the building blocks of planet formation. Maybe not the planets themselves, but if you can collect all the material together and sort of get it into a reasonable size early on, then it can then continue growing to form the planets later on, and in time before the gas disk disappears. So that's sort of the thing we're looking at. And then there's instruments like ALMA or the sort of ALMA interferometer that can actually now observe quite high resolution, observe these young stars at quite high resolution. So we're kind of interested in what are the conditions that would allow ALMA to actually see this happening, if it is happening. So we're trying to understand, could you actually see this, and what would the characteristics of a system where you might see this be? So could you predict, okay, there's a very young star and its properties are this, so if you were to sort of focus on that one, you might start to see these kind of things going on. So we're trying to understand what would you see, and could you see these processes actually taking place these days? So that's one of the things we're trying to understand there.
Wow. It's just so cool that you can now look at young stars forming in the galaxy and be able to infer lots of different information from that.
So I mean, in particular ALMA, which now, so it's observing mainly in the sub-millimeter wavelength. So, I think up to 1.5 millimeters and down to maybe half a millimeter sort of wavelength. And that's sort of the wavelength where you expect sort of millimeter-sized dust grains to be emitting a lot of radiation. And so it's got such high resolution, you can start to see structures in these disks around young stars. And virtually all of them have some kind of structure. We're not sure why. Could be that there's already planets there that are sculpting the disk. But we're also interested in maybe trying to probe even earlier stages, probably before the planets formed, and try to see how the structures in those disks might be influencing how the planets then get built. So,
yeah, that's so cool. So what kind of things have you found from your research so far?
So at the moment, it's still mainly theoretical, and a lot of the work is highlighting how difficult this is. So there are a couple of systems that people have observed that appear to have spiral waves in them, and certainly lots of the disks have some kind of structure. It's still not entirely clear what's causing this. Is this some kind of instability that's producing spirals, so hence the kind of thing we're interested in? Or is it just something went past and perturbed it and created a spiral-like feature that isn't actually something that's long-lived and didn't actually grow out of some instability? So, there's observations that are hinting at this, but we haven't yet really definitively seen something of a very young system that tells us that's actually happening. So we're trying to understand a bit better about whether you can see it and when is it most likely to see this kind of process is taking place. So we're still not sure. So that's sort of why it's interesting. We're still working on that.
Yeah, absolutely. And like you said, there could be different causes for this spiral gas disk that we don't know. So how can you tell between it being what you think it is?
So for example, one idea is if the spirals are sort of internally generated, so the disk is unstable and it forms spirals, then you'd expect it to be symmetric. But if, for example, they come from some passing star that perturbs the disk, you might expect it to be not symmetric, because of course the star passes on one side, so it perturbs one side of the disk more than the other. So there are some ideas as to how you might distinguish, say, a spiral that was triggered by, say, a passing star, or maybe a planet inside the disk versus a spiral that grew out of some instability in the disk. So there's some ideas. We don't have enough observations to rule them out, but we do have some ideas about how you might tell whether this was a spiral from an instability that's been there for a while, a bit like in a disk galaxy, or is it just something that got triggered by some passing star or maybe a planet in the disk. So we're not sure, but we think we have some ideas of how you might tell the difference.
Yeah, it sounds kind of exciting that seems so current and it's still kind of developing in its early stages.
So these kind of observations that can see at this kind of level of detail have only really happened in the last couple of years. So it is very current, and there's a lot of interest in trying to, because you're trying to probe earlier and earlier in the star formation process to try and see, ideally you'd like to maybe almost try to see some planet forming, which is possible but quite difficult. But that's the idea, is to get really early and start to see processes that are probably involved in both feeding the star, because of course the star has to grow, but also involved in building the material that then forms planets later on. So there's a whole lot of interest in terms of some fairly fundamental questions about how do stars form, but how do planets form. So they're both related to each other, we think.
Yeah, that's so cool. From the way that it's been developing quite quickly in recent years, where do you think it's going to go in the future? Do you think it's going to be developing at the same pace? Do you think we might actually be able to see planets forming? I mean, it takes a long time, so we might not be able to see them.
Yeah, I think so. Of course, you're right. You only see a snapshot, so you can't see a planet actually growing in a disk, because we can only see it for a short amount of time, and we can't observe something for hundreds of years to watch it grow. But you can look at lots of systems. ALMA is probably the system that's the most exciting at the moment. So it'll just keep collecting data and get more and more information. There are other projects aimed at trying to see, these disks at fairly high resolution and high sensitivity. So I suspect we're not going to see another big leap at the moment. I don't think there's anything planned that would get much better, but I suspect over time we may see something like that. But for the moment, I suspect we're just going to see more and more observations as they probe different star-forming regions, and we'll hopefully start to build up a picture of what's actually going on. So I think that's what I would guess, is we'll just keep collecting data and trying to see. As we look at more and more systems, hopefully we will start to see something emerging that we can then understand with the theory that we're doing.
Yeah, absolutely. And that is kind of the goal of the telescopes that we send up, the ones that we use on Earth, is to probe more of the universe.
Exactly. So we want to especially when you're doing something like this, where especially star formation, you look at, because star, for a sun-like star, okay, it takes about 50 million years to end up as a proper star with nuclear fusion in its core, but a lot of the building of it happens fairly quickly, like within a few million years, right? So when you're looking at star forming clouds, you're looking at either multiple clouds, each of which are a different age, or you're looking within a cloud, there's a bit of a spread in age. So you're never quite sure at exactly what phase it's, because it all changes fairly quickly. So you really want to get into the very young systems, but that's really quite hard because they're still quite heavily embedded in their gas clouds. And you go a bit older, but it's changed quite a lot. Even if you go maybe a million years older, the system's changed quite a lot. So you can't always say, well, we know a lot about the very early stage by looking at the slightly later stage, because actually they evolve quite quickly. So you just want to try to get, I'm not explaining this very well, but you want to try to probe as early as you can, but there's a limited number of targets and a limited amount of time, and all the observations take time. So over time we'll build up a bigger and bigger picture, I think, of what's going on.
Yeah, exactly. And as you say, like, there'll be loads of different stars that are at different stages,
yes,
so hopefully we can make loads of observations of them.
That also helps a lot. If you look at different stages, you can see patterns emerging, and this is how they evolve. But you need a decent sample at each stage to try and see what's the typical at this age and what's the typical at that age, and try to build up a picture. Because even within each age, there's variability. They're not all exactly the same. They're not all the same type of star. They don't have the same mass. They didn't form in the so there's patterns, but there's not exactly the same for every single one.
Yeah. So. And that sounds quite fascinating for me, that each one's different, because it makes it kind of, I guess, a bit more of a challenge.
So I mean, the big picture is fairly robust. You've got a big cloud of gas and dust. It starts collapsing. It's rotating, so you start to form a protostar, but then the conservation of angular momentum means that a lot of the material falls into a disk. That kind of picture is fairly robust. But of course, how big is the disk? How massive is the disk? What's the mass of the star in the center? Things like, what was the metal content of the cloud? Is it metal rich, more than the sun? Is it metal poor compared to the sun? Is it the same as the sun? That can influence, how it heats up and cools down. Is it a very dynamically violent? Are there lots of stars forming in the same region, in which case they're interacting and knocking each other around and dispersing stuff? Or is it quite quiet, in which case they sort of form in isolation? So there's a whole variety of things that can influence precisely what happens, even though I think we have a reasonably good idea of the basic picture, but the details for each system can differ depending on the environment it's forming in and all sorts of things like that.
Yeah, exactly. And that just seems quite interesting, that all these different factors kind of come together to then build the star's life cycle. And so what intrigues you so much about studying these star formations?
So I guess the thing that was motivating me initially was this idea of trying to link it to planet formation. So when I started doing this, which is now quite a long time ago actually, say 18 years ago or so, I mean, we just started finding planets around other stars. So the first sort of planet around a sun-like star, other than the sun, was 51 Pegasus B, which was 1995. So I started working on this maybe 2001. So we had a sample, but not a very big sample. And so, of course, there was a lot of interest in trying to, we now knew there were planets around other stars, We were starting to see observations of young stars with disks. And so there was this sort of understanding that you had this process, which I guess we'd known about for a long time. And the standard solar system formation was always forming in a disk around the sun. But now you actually had planets around other stars. You actually had observations of disks around young stars. And so people were trying to think about, how do these planets form? And then early on, there was this problem that when you, say, did a basic calculation of, say, how long it would take to form Jupiter, people say, well, maybe 8, 9, 10 million years. And then people said, but hold on, when we look in star-forming clouds, the gas is gone within 5 million years. So how do you form Jupiter if the gas goes away faster than the planet can form, right? And so then lots of people said, well, okay, but maybe something is happening to speed this up. Maybe there's an instability or something. And that's what got me into thinking about this. And a lot of people saying, well, maybe the planets, rather than forming from the bottom up, but dust grains collide and grow, and then eventually you have like an Earth-type planet, and then if it gets big enough, it catches onto the gravitation, onto the gas, and you form your Jupiter or your Saturn. Maybe they form directly. Maybe they form like stars. Maybe the disk material just collapses gravitationally, and you form these gas giants. And an awful lot of what I've done is basically to say, no, that doesn't work. But there was that interest at the time about if the standard process appears to take longer than the lifetime of the disk, then something else must be happening. And so, I worked on that. I still work on that, but, a lot of the stuff has said, actually, this doesn't really work. But other processes have sped up the planet formation process. We don't think it's as much of a problem to form Jupiter quickly, but clearly a lot of things are happening very early on. So it's still interesting to keep looking at that very early stage of star formation to try and see, what's going on here that allows a planet like Jupiter to form so quickly. Because the Earth doesn't have to form that quickly because it doesn't have a lot of gas. It can be forming from the remnants, much more slowly. But it's something like Jupiter or Saturn, we're fairly confident has to form pretty quickly, because if it doesn't, there's not enough gas left in the disk to form the envelope, right, to form the atmosphere of the planet. So there's still that interest in, say, trying to understand what processes that happen around very, very young stars are aiding the formation of planets. And I guess it's partly motivated by the fact that we now have so many planets around other stars. We know they're almost ubiquitous, right? There's planets around virtually every other star out there. Planets of one kind or another, right? So not all gas giants, but still gas giants are still quite common. Maybe 15-20% of all stars have a Jupiter-like planet around them. So it's not like forming Jupiter is rare. It happens fairly commonly. So it's useful to understand what process is helping these big planets to form fairly quickly.
Yeah, that sounds absolutely fascinating. It's kind of exciting, almost like a problem to be solved.
It is still, and there's still a number of. So we know that when you form a disk around a star, there's lots of small dust grains, and the question is, how do you get those small dust grains into big boulders? And there's a number of problems. One is when they get relatively big. When they hit each other, they should just fragment and break apart, right? So what is allowing them to stick together, right? That's one question. Nobody quite knows that. The other problem is that when they're in the gas disk, they should be undergoing a sort of inward drift from aerodynamic drag, and that can get very fast. So how do you stop all these things from just drifting into the star? So there's still a number of things that people don't fully understand. We know that you must be able to turn the small dust grains into big objects because we're here and there's lots of planets. Yeah. We're not entirely sure of what allows them to get through those hurdles where you think, they should collide and break apart, or they should be spiraling inwards very fast, but they're not. We're not quite sure what, you could just say, well, we know it works, but we'd like to understand, what's allowing these things to grow so efficiently in these disks. And that's one of the reasons why it's still interesting is how do you explain where the physics is saying something like, well, this should be difficult, and yet the observations are saying actually it should be quite easy because there are all these planets out there. So that's kind of the interest.
It's interesting to see the reasoning behind it, and that's kind of almost what drives physics, because as you say, like, we know it works because we are here, but it's we want to know why and
exactly.
how and the reasoning behind it.
Yes, I think that's right. I think somebody was telling me this the other day, a lot of the time people are happy with something works. But as physicists, we often want to say, well, why does it work? Because it works, and that's maybe good enough in some cases. But if you really want to understand the world around us, then you've got to do better than just it works. You've got to say, okay, let's try to work out why it works. What's allowing it to work? What are the underlying processes? What physics is taking place? And that's sort of the same kind of thing. We know that planets form. There's lots of them. We'd like to understand the processes involved in that, just so that we can feel as though we understand the whole sort of planet formation process, and not just saying, well, okay, it works. Something deeper than just that.
Yeah, and I know you mentioned that you are part of a team that finds exoplanets or planets from other star systems. So has finding these other planets helped with understanding how planets form?
So
why?
Yeah, so a lot of what we've been doing, and if you know, there's the NASA Kepler satellite that they just stopped using, and there's a new one they've just launched. So it was very successful at finding planets that transit, the ones that pass in front of the star, and so they block a bit of light, and then you can measure. If you know the size of the star, you can get the size of the planet, and hence you can get the radius of the planet. And of course, not all planets transit because it depends on the alignment. But they looked at about 150,000 stars, and they found about 2,000 planets. Now there's many more planets around those stars, but they found the ones that transit, right? The ones that happen to pass between us and the parent star. And what we did a lot of the time, not only this, but we would just follow those up. We'd stare at the same star, and if you can then measure how the star's moving in response to the planet, then you can then use that to get the mass. And so the transit method, which the satellite was using, gets the radius, because it looks at the change in brightness of the star. And then the sort of Doppler wobble method that we use, which is just to measure the change in velocity of the star, you can get the mass. And so from mass and radius, you can then get, say, internal composition. You can tell if something's a rocky planet, or whether it still has to have a lot of gas, or whether it's a water world, and things like that. And I guess it hasn't played a big role in, say, trying to probe, how they form in the early stages. But there are some interesting things that have come out. So, for example, there's a number of very small rocky planets that we found, and they're very Earth-like. If you put them on a composition curve, they look like they have the same composition as the Earth. But they're very close. So Kepler 78b, which is one of the first ones we reported on, it's only like 1.8 times the mass of the Earth, and it's only 20% bigger. So it's very much the same kind of size. It's like twice the mass, but it's still quite impressive that you can detect something that small. But it's got an orbital period of 8.5 hours. So it's very, very close. And the star's like the sun, so it's a hot star, and this planet's very, very close. So there's clearly no way that it could be habitable, right? There's not a chance. But you can take these, and you could do a simple thing and say, well, look, all these rocky planets close, and we could extrapolate out, and we can show how many we'd expect to find, say, at the same distance that the Earth is from the sun, right? And if you did that, you'd get quite a lot, maybe 10% or 5%. So it's quite a lot. But then people noticed that, hold on, if you go up in radius, you discover that predominantly all the planets that have radii less than 1.5 times the radius of the Earth are rocky. But when you get above 2 Earth radius, they all still have big gas envelopes. They're still quite gaseous. They're a bit like Neptune or something, small Neptune. And so the question was, well, why is that, right? And the solution seems to be that what's happening is that if you have a small sort of Neptune-like planet very close to its star, the star will strip the atmosphere off. And what you're left behind is this rocky object, right? The terrestrial-like planet. And so it's distinctly possible that this population of rocky planets that we find close in is not actually the inner population of rocky planets that goes a long way out. It's the inner population of planets that were bigger earlier on. And so you have to be very careful of extrapolating those out, because you're not extrapolating the right population. So things like that. So people are very interested in, say, how many planets are probably in the habitable zone of a sun-like star. So where they could, I don't like the habitable zone very much because we don't really know what it is, but let's say a region where they could have liquid water. And of course you could just simplistically extrapolate the known population of very close and rocky planets out to those kind of distances. But if those are actually the a population that were once like Neptune or mini Neptunes rather than primordially rocky, then that's the wrong calculation to do. And so you then have to be very careful about how you do the extrapolation. So it's an interesting issue as to, can you use the inner population to say something about habitable planets around these stars? And the answer is maybe not yet, because we don't really know where those rocky planets come from. And there's a strong indication that they probably weren't rocky originally. They just become very heated by the central star and lost all their atmosphere. So there's things like that as to, trying to understand. I guess I'm waffling a bit, but helping us to understand, how do planets form initially? Do they form rocky, or which ones form rocky? Or so, for example, the most common type of planet we now find is what we call a super Earth. So planets that are about 1.5 to 2 times the radius of the Earth. They're very common. So if you look at the occurrence rates, you've got, I forget the numbers exactly. So, out of all the planets that we found, so we've got like 4,000, maybe 100 like Jupiter, or 200 like Jupiter, maybe 100 like Saturn, and then it gets a bit harder to find them. And there's maybe a couple of hundred that are quite similar to the Earth, and then there's like hundreds that are just twice the size of the Earth. Not exactly twice, but in that region. So these super Earths, which we think are planets that probably formed with a rocky type core similar to the Earth, but with quite a dense atmosphere, a bit like Neptune. Very common planets. And so that's also surprising. They're not in our solar system. We don't have any in our solar system. But around other stars, they appear to be the most common type of planet. So it's things like that, trying to understand what does that mean, and what does it mean about planet formation and things like that. So
yeah, that sounds really interesting to then find out so much about these types of planets, and kind of surprising results, especially with the super Earths.
Yeah.
So why do you think they are the most common type of planet out there? What are the current theories about why?
It's a good question. I'm not sure that there's a good answer to that one yet, because the standard picture was that your big planets that retain, say, atmospheres like Uranus and Neptune and Jupiter and Saturn, they formed a bit further out where the disk was cold enough that you collected ice onto the dust grain. So you actually had slightly more material out there, and you'd form your big rocky core earlier. And in fact, your rocky core would probably be a mixture of rocks and ices and stuff like that. And then it gets massive enough, quickly enough, that you can then attract all the gas, and you end up with a gas giant or an ice giant, or whatever you want to call those planets. With these ones, if the inner rocky ones are the stripped cores of what were super Earths at an earlier time, well, their composition is very like the Earth, which kind of tells you that they didn't form out there where it was icy, because you're not seeing their composition being quite dominated by water. They very much have a composition that looks very like the Earth. So 30%, dense iron and nickel, and the rest magnesium silicate. So somehow we think that means they probably form closer in. But if they form closer in, they should take longer to form. So how did they then get the gas that was there, that was then potentially stripped if they got very close to their star? And so there's quite a lot of debate about exactly what this means. And it's not quite clear. It's maybe we've misunderstood planet formation a little bit. Maybe planets can form closer in than we thought, and faster than we thought. Maybe the solar system is rare. That's the other interesting question is the solar system, because we have all the big gas giants further out and the rocky ones inside, we thought that was a nice picture. But maybe that's just because it's what it had to be for us to be here to see it, right? So maybe the solar system is an unusual configuration, and that lots of other systems are very different. And so, but it does look as though these kind of objects that are maybe twice the radius of the Earth, and maybe 5, 6, 7, 8, 9, 10 times the mass, that still retain quite gaseous atmospheres, the things we call super Earths, are actually very common. So probably understanding them will help us to better understand planet formation. But I don't think there is a well accepted idea yet as to exactly how they form, because it is a little bit surprising that things that you'd think should form further out are much closer in and appear to have cores that are actually properly rocky, not icy. So that's a little bit confusing, but it's an interesting puzzle.
Yeah, it sounds so exciting. All these puzzles and problems that are still left to be solved for future generations and for current researchers that are part of it.
It is an amazing field in terms of how it's, because the first planet around another sun-like star was 1995. So what's that? Was that right? 25 years ago, 24 years ago.
Yeah.
So it's remarkable how it's changed in a relatively short space of time, and our ability to find and characterize these planets is quite something now. We can measure. So for example, when we're looking for say, trying to characterize a rocky planet around a sun-like star, which, say, Kepler-78b was a classic example. It's very close in, so of course the reflex motion of the star is bigger than if it was further out. But even so, the star is only moving away and towards us with the speed of about 2 meters a second. So you can walk at that kind of pace, right? So maybe that's a little bit of a fast walk, but it's not very fast. And so we are able to pick out that signal that's only a couple of meters per second in size around a star that's quite noisy and, you know, lots of other things, but you can still extract that information. Whereas, you know, 20 years ago, you were mainly looking for things where the star was moving at maybe 10 or 20 meters per second. We've managed to get the instrumentation down to the point where you can actually see those kind of really small radial velocity motions of this central star in order to try to pick out the mass of the planet. So it's very impressive what we've been able to do in the last 20 years or so, what the scientific community has been able to do. So
yeah, absolutely. And do you think that we'll be able to, or obviously there are hopes that we'll be able to develop this even further, so we can find even smaller radial velocity
that's really hard. So if you wanted to find, so Jupiter around the sun induces a radial velocity in the sun of about 13 meters per second. So that's fairly easy, but it takes about 11 years to go around once. So you have to wait quite a long time to see that kind of signal. Now the Earth going around the sun obviously takes a year, but the radial velocity amplitude due to the Earth is about 10 centimeters per second. So it's really tiny. So that's just the noise, the stellar activity, all those kind of things that can influence, because you're basically looking at spectral features on the star, and they can be, so, you know, Doppler effect, the spectra shifts, you've done this, I guess, spectra shifts back and forth. If something goes away from you, it moves to the red, it comes towards you to the blue. And so we're basically looking at lots and lots of spectral lines and trying to see a very tiny shift back and forth as the star's moving away and then back towards us and away and then back towards us. But of course, you can also get those what appear to be shifts if the star's surface is noisy. So you have star spots or ejections or whatever's going on the surface can make the spectral lines appear to be moving. And so that's a problem that you have to try to work out. And the kind of effective amplitude of that is about 1 meter or 2 meters per second. So if you just had a star with no planets around it, a bit like the sun, you'd probably expect to see radial velocity variations of a couple of meters per second. Now you put a Earth-like planet at 1 astronomical unit around that star, it's putting a 10 centimeter per second perturbation on that. And you've got to now pick that out of all this noise. And there's a lot of work going into that to try to understand, can we characterize the sort of stellar activity accurately enough that we can then start to pick out these very small signals. And that's one of the reasons we've managed to go down to maybe radial velocities of only a couple of meters per second, because we now have a better understanding of how the stellar activity influences the signal. But going down to 10 centimeters per second is quite difficult. The one saving grace may be that most of the stellar activity happens on a timescale of, say, 20 days or 30 days or something like that. Whereas if you're looking for a 1-year signal, it's much longer. So you may be able to separate out the long period signal from the planet from the shorter, but still, it's still trying to find a signal that's only 10 or 20 centimeters per second when the noise from the star might be a couple of meters per second. But there's a lot of work going into this. With TESS, which is the latest NASA satellite, the Transiting Exoplanet Survey satellite, which they launched last year, I think, that's going to do a lot of work with M dwarfs. So M dwarfs are stars that are less massive than the sun, and they're cooler. And so the region that we'll call the habitable zone, which I don't really like the term, but let's say the region where liquid water could exist on a planet is closer to the star. And so if you had an Earth-like planet orbiting that kind of star, not only is the star a lower mass, but the planet would be closer, so the effect on the star is much bigger. And so TESS will probably find quite a lot of rocky planets around M dwarfs in a region where there could be liquid water on the surface. And because the motion of the star will be bigger because it's a lower mass and the planet's closer, we may be able to start measuring that one. So we may not be able to truly definitively find an Earth-like planet at 1 AU around a sun-like star, but we may find Earth-like planets in what we'll call the habitable zone around lower mass stars quite soon, and then we'll be able to characterize those. And that becomes interesting because they potentially they could have liquid water, and if they have liquid water, then maybe there could be life on them. There are some caveats, of course, because a planet in the habitable zone of an M dwarf is a bit like the moon around the Earth. So it's synchronous, so it's tidally locked. So one side of that planet will always face the star, and one side will always face away. So what happens to life on a planet where one side's always irradiated and one side's never irradiated? We don't know. And of course, the star's lower luminosity, it's fainter, it's cooler, and so the sort of typical wavelength of the light's going to be different from the sun. So we don't know what's going to happen there, but it's still interesting that we'll probably have a reasonable sample of rocky planets orbiting stars less massive than the sun in a region where liquid water could exist. We'll probably have that fairly soon. But whether we can actually say anything more than that, I don't know.
Yeah, that sounds like a very exciting and kind of new time for discovering exoplanets and planetary systems. There's a lot of satellites and telescopes now being launched and in coming years by both NASA and ESA. What do you think will come out of all these telescopes? What do you hope will come?
So I suspect the NASA one that launched last year, TESS, that will probably find a lot of rocky planets around these lower mass stars. So that'll increase the sample of those a lot, and we'll be able to follow up some of those with radial velocity measurements and get the masses and the radii. So it said something about the composition. JWST, the James Webb Space Telescope, launches in 2021, we hope. And that will probably allow us to do some kind of spectroscopy on planets. Now, one way you can do that is just transit spectroscopy. You observe the spectrum of the star and you try to work out the difference between what it looks like when the planet is passing in front of it and going behind it. And that way maybe say something about the spectrum of the planet's atmosphere. You can do phase curves. So, as the planet goes around, if it's got no atmosphere, then basically it'll get hot on one side and very cold on the other side. But on the other hand, if it's got an atmosphere, then it'll spread that heat around it. And the sort of, if you then look at the apparent luminosity of the star, what you see when you combine the planet's radiation and the stars depends on how much of an atmosphere it has. So you can start to say something about whether planets have atmospheres. So we'll start to say something about or we've got a little bit about planetary atmospheres, but say more about planetary atmospheres. But still probably not something along the lines of, what's the atmosphere like of a planet in the habitable zone around an M dwarf. That's going to be tricky, but we'll start to be able to probe atmospheres a little bit more than we have before. And then Plato, which is the ESA mission, launches in 2025 or 2026, and that's going to look at lots and lots of stars. And the idea there is to try and find a true Earth analog, so one Earth mass roughly at 1 astronomical unit around a sun-like star. So that's probably going to be, I don't think TESS will do that. Maybe an outside chance that TESS will do it, but I don't think so. But Plato's plan will be to search enough stars for long enough to definitively find the transit of an Earth analog, a true Earth analog. And then it begins very interesting, because now you really are talking about something that's potentially really similar to the Earth. It's around the same kind of star, it's at the same distance, it's got the same mass, it's got the same radius. And then ideally, now of course, at that stage we probably won't have the instruments that would allow us to properly probe such a planet's atmosphere, right? Because it's very difficult. But I suspect we would then put more effort into developing instruments that would allow us to then properly look at a planet like that and say, okay, can we get a spectrum from that planet? Can we say something about its atmosphere? Does it have water? Does it have oxygen? Does it have ozone? Does it have CO2, etc.? Does it have methane? And try to infer something about that. But I suspect that's quite a long time away. So Plato's the sort of mid to late 2020s, so we probably know about these planets in the late 2020s. Then we've got to think about building something that can actually properly observe such a planet, and so 20 years away. I've often said that I suspect nobody should believe any habitability claims for the next 20 years or something. I think people will probably make them. I'm not sure I believe them for a while, because it's going to be so difficult to make these kind of observations. And we really don't know what a biosignature is definitively, right? We don't know that if you see water in an atmosphere or oxygen, or that it's definitively a biosignature. There's lots of abiotic ways to do that as well. So you've got to be very careful. But I think, 20 years' time, we may have the kind of observations where we can make stronger statements about something like that. That's the hope, I guess.
Yeah. And is one of your drives to keep discovering exoplanets then to also search for life or habitability on other planets?
Yeah. So I think personally I like just doing physics. I like the idea of trying to understand, say, how planets form, and I like the challenge of trying to, work with a team that tries to find them or characterize them or take the measurements. It's just fascinating. be able to do that and to try to think about, what does this mean in terms of star formation and planet formation. So I'm personally, more interested in just trying to use it as a way of doing physics, if you like. Of course, the long-term goal, the one that we probably have to strive for, because it's the way that you capture the public's imagination, is to talk about, can we find something like the Earth? Can we then probe something like the Earth? Can we determine if something like the Earth around a different star has life? Can we say something about the complexity of that life? That's probably the long-term goal for the community, because that's what I think. It's a fascinating question, and of course, people are rightly fascinated by the idea of whether or not there is life around another planet, or life on another planet around a different star, or even life in our own solar system, right? But then, personally, I like the challenge of just trying to understand things, and planet formation and star formation, and doing physics rather than chasing after this habitable exoplanet. But I suspect that is kind of the way we will be doing things, is because, and along the way, we'll ideally be doing good physics and good science, because that's why we do it. But at some level, we're trying to get to the point where we can say something about another Earth-like planet around another star, and what we can say about that. But you have to bear in mind that we're physicists who are trying to understand things and not just chase after this one thing. But that is probably the way we will eventually go.
I guess, yeah, you are right in that the main goal of maybe the public, or the general public, is life, because I guess aliens really capture the public's imagination. Yeah. But I mean, you are right in saying that, or physics, just doing it because you love physics, you enjoy the problem solving, the questions that come out of it, and trying to think about them, it's kind of nice to hear. And
I've always worried that I'm insulting the public a bit, but it's also nice that if you do find something interesting. I mean, we had one recently where the planet was extremely dense, and suggested it must have had some kind of collision that knocked a lot of material off, leaving the dense core behind, you see. And that got a lot of coverage. So even though I suspect ultimately the bigger interest is in, can we find life on another planet? Can we find an Earth analog out there around a sun-like star? The public is still interested when you find something interesting about a exoplanet, or we found a multi-planet system, or this particularly dense one, or this particularly hot one, or something, whatever. It's not as if the only thing the public's interested in is this one thing, but you can tell that obviously what's keeping the public interested in the bigger topic is probably, can we eventually find life on another planet around another star? But it is nice that you work in a field where when something interesting happens, you can put out a press release, and there's quite a lot of interest in it, because it's an interesting topic in itself, even if the deep down the interest is maybe to do with life or something like that. But
yeah, and I know you've mentioned that you, as I said, you like the problem solving, you like just the general interest in physics. Is that your favorite thing about being a researcher?
So I mean, I most of my time, even all the way from studying, I guess, has been to just do things that I found interesting. And I was lucky enough to be able to do that. So I've never had some kind of grand underlying research plan. I just like the idea of here's interesting and challenging problems, and I've been fortunate enough to be able to work on some of them. And so yes, it is that aspect that I like, is being able to get involved in something interesting and then try to understand it using physics and using various other skill sets, I guess. So yes, it is that sort of problem solving side I like more than the idea of, it's the challenge of doing it, I think I like more than, say, some end goal. I don't have some sort of plan to say I'm going to be the person who solves this puzzle. No, I'm just enjoying tackling interesting problems and trying to work out how to solve them, rather than saying, I'm going to find the first habitable exoplanet or something. That's not really the goal. I think I'm much more interested in just doing something challenging and interesting, and trying to tackle interesting problems.
Yeah, and I think that's kind of why quite a few people maybe get into the subject in the first place, because they like the sort of challenge it presents to them that maybe they haven't found with other subjects, or that they just feel enotices them, or creates that interest and drives them a bit more.
I think most there's lots of interesting problems with sort of research career structures, but mostly I think researchers are quite fortunate to be able to spend some of their time just thinking about something or working through something. It's hard to imagine another job where you can just spend hours at a time just trying to tackle this interesting problem. Nobody's breathing down your neck to deliver some specific thing at some specific time. You're just trying to solve something, and it's something you're interested in. And I think it's amazing that we're able to do that kind of thing. And it's great when you suddenly realize, I know how to solve this, or you get it, or you fix the problem, or you get a solution. And it's just a great thing to be able to spend your time thinking about problems like this and trying to solve problems like this. There's not many jobs that let you do that, I think.
Yeah, absolutely. And that's kind of, I guess, what interests me about a research career as well, because I'm like, oh, that kind of sounds real nice to be doing in the future. And it's a privilege that kind of only researchers get, almost, sitting around and thinking about problems that really
I think that's true. I think there are some areas outside the more formal research where similar skills are used. Certainly parts of the industrial sector needs people with data analysis skills and problem solving skills and computational skills and all these kind of things. So I think there's probably lots of challenging jobs outside. Maybe not many where you get the freedom to decide what problem you'll tackle, right? And you can just go, I'm going to work on. That's one of the nice things about research is you do have a lot of freedom to say, what is the problem I'm going to work on. People aren't, okay, maybe when you're still starting out, you're working with other people, but even then, a lot of places want even early career people to develop some independence and to come up with their own questions, to tackle their own problems. And that's maybe the bit that's slightly more unique, because there's maybe plenty of places where you'd have to write code or deal with data sets or develop data analysis techniques, and it's challenging and it's interesting, but maybe it's a bit more structured than, say, in a research environment where you can often have your own freedom to decide which problem you'd like to tackle and how you're going to tackle it and how you're going to do that. And it's very nice to have that kind of freedom.
Yeah, absolutely. And as you've said, or we've kind of discussed, you work as part of a team as well for some of your research projects. How do you like working in a team? Like, how is it different to then working as an individual?
So it's interesting because because it's fairly new to me. So for a long time, I just worked, with people. I run my own research, and either with students or postdocs, or maybe a collaborator or something. And it was very small, and you had your own time scale, and you could do your own thing, and you just kind of would talk to somebody and say, it's an interesting problem, let's work on that, and have a go. So working in the team is slightly different in a way, because of course it's a bit more structured, and there's a bit more planning and thinking about exactly what we'll do. It's still, I'm quite fortunate in many respects, because this team is not that big. And so the way they tend to work is say, okay, here's an interesting target that we're going to observe. Who would like to look at this one? And so people will go, I'll do that one. And then they have quite a lot of freedom to decide how to tackle it. And of course they will send around drafts and people might respond and say, actually, no, you should probably do that instead. And they get lots of advice, but they can run it relatively independently. And when they need something from another member of the team, they can say, okay, can anybody do this for me? And then that person does it, and they collaborate in that way. So it's still fairly nicely done. It's not very structured in that sense, even though there's a lot of expertise. So of course, if you don't know how to do something, you contact somebody else, and they either do it for you, or they say, no, you do this and that and that. So you get a lot of advice from people. But once you're sort of looking after a particular target, then you get to set some of the parameters, the timescale. When do you think you'll finish? How long will it take? How many more observations should they do? When should they do the observations and stuff like that? So you do get a fair amount of independence, even though it's part of a team. So it's quite a nice team to work with.
Yeah, that sounds really nice. And because I've also taught with Professor Victoria Martin. Yeah. She works as part of a very big team working with CERN. Yeah. And she's also said she loves the collaboration, the fact that it's a really big team. But it's nice to have a bit of a working with a smaller team's perspective as well. Cause there's differences, and some people prefer others. And
it is, and I mean, certainly my experience with this team is it's quite good at looking after students. So if the students working on something, then they protect them and they make sure nobody else works on it. if there's students who need work, then they try to find a project for them to work on. Say, okay, you need something for your thesis, then why don't you take over that one? And or maybe the reverse, actually, you need to focus on that one, so we'll take something away from you, so that you can actually finish that one and write it in your thesis. So they're quite careful about making sure that the early career people are given things to do that they can then work on. It's very collaborative, very supportive, and it's nice to work in a team like that.
Yeah, and it sounds like a really nice team to kind of start out with.
Yeah.
That's how
That's very good. Yeah, quite a
students.
few early career people have been in our team and done very well because we try to make sure that they get interesting projects to work on, that they can lead and they can take sort of some charge of it. It's good.
Yeah, and it's absolutely almost necessary to build up those skills from the go,
exactly,
so that they can go on and become successful, like you said.
And sometimes the techniques are changing quite fast at the moment, and so often you end up with the early career people being the ones who understand them best, and so because they're the ones who work on them, the more senior people might know something about what the kind of idea of what needs to be done, but it'll be the early career people who are actually getting into the nitty-gritty of doing that, and so they then become the experts at something, which is nice to see as well.
Yeah, and I guess that's how it then progresses to become more developed in the future.
Right. Yeah, that's right. Yeah,
that's brilliant to see sometimes.
Yeah.
So, speaking about students and early careers, what kind of advice do you have for undergraduates that are currently going through physics degree or just in general a degree and maybe a bit clueless, maybe they want to go into research? So what kind of advice do you have?
It's difficult in a way, because certainly long term the whole sort of academic research career is very tough, because there's a limited number of jobs at the end, and there's quite a lot of people at the beginning, and so it's quite challenging. So my own, I don't like giving advice because I always think everyone's different, but my own experience was to just do what seemed interesting and worthwhile at every step. And so I finished a degree and had the chance to do a PhD and thought, okay, I'll do that. And then finished a PhD and then had an opportunity to do a postdoc and thought, okay, I can do that. But it wasn't sort of planned. It's only maybe later on where I went, okay, I really need to think about this now. I've got to start planning something. But initially it was kind of just interesting, and I got to work in different places, work in different groups. I changed topics a little bit. And everything was just done on the basis of, this looks like an interesting, worthwhile thing to be doing for a while, and go from there. And I feel very fortunate that I can still do it. But it is a challenging kind of career path. On the other hand, the overall skill sets are incredibly valuable. So there are lots of options for people. So it's not like you get to some point and everything ends. No, you just get to some point and something you go and do something new, and it's many cases can be just as challenging and it's interesting. But I think it's worth being aware that the whole long-term research career structure is quite difficult, and there's a lot of very good people who will be looking for jobs and funding and research fellowships, and lots of very good people don't get them, unfortunately, and that's always quite difficult. But there are things you can do. It depends on I was trying to think of how to say this, because I think the community is trying to think harder and harder about how you deal with people who might not be as flexible. So like if you have the ability to go anywhere, then often you can get a job. If you're willing to go to Germany or America or Australia or Brazil or whatever, South Africa, Holland, there's lots of options if you're able to do it, but not everyone is, and so it seems unreasonable that the way to build a career is to be willing to travel the world, right? So that's probably still true. I think the academic community is trying to think a bit harder about whether that's, how do you take into account the fact that some people can't just go off and, work in another country. They may have some responsibility here that means that they're slightly constrained. I'm not sure we've solved that problem yet, but people are thinking a bit more about it. But on the other hand, it is great. And if you are, if you enjoy the research and then I think as long as you're enjoying it, that's maybe the first step towards, doing it.
Yeah, absolutely. And that's I've said it before when I've been recording these episodes. That's one thing that I really try to promote to people whenever they're kind of thinking about the future, is just do what you enjoy at that
Yeah,
moment,
yeah,
and
yeah.
it'll kind of fall into place. As you've said,
Yeah.
your career has kind of gone like you're just
Yeah.
kind of going along with it almost,
Yes.
not really having a plan, but because you found it interesting, you kind of
Yeah.
just continued on with it, which is something that I really advocate to my friends.
I think the one thing I
like,
did do, which I still think is quite useful, is there's nothing worse than coming to the end of a research contract and not knowing what's coming up.
Mm-hmm.
And so something I did try to do was to have the next stage in place well in advance. You don't want to be like 1 month away from the end of a contract and then go, what do I do now?
Yeah.
So it's a bit annoying because you end up applying for jobs or applying for fellowships maybe 2/3 of the way through something that you're enjoying. And so you're thinking, well, I'm applying for something new and I'm still enjoying doing this one. But it's kind of worth doing because you don't want to be waiting until the very last minute and then going, oh, I don't have anything to do now. Yeah. And of course, it gives you the other thing. If you don't get something, then you know that you're going to have to make a decision at the end. You know, it's because you want, not you want. I always thought I need some idea of what's going to happen next. I didn't mind what it was terribly, but you want that ability to say, okay, I've managed to get another position or a fellowship, so therefore I'm okay for another few years, and then So it's worth thinking about planning a little bit, even if you're enjoying what you're doing, being aware of what's the next stage going to do. I think that's worth thinking about. But that's just me, I guess. That's what I did.
Yeah, no, that's brilliant advice, because I feel like everyone should also have that plan. Like, I do say, maybe go with the flow and just do whatever you enjoy. Maybe have a bit of a plan. Maybe exactly. As an undergraduate, personally, I have 3 more years after my degree.
But even as an undergraduate, you can think about what research projects you're going to do. And I worked with one who did an undergraduate project with me 1 year, and then he did something completely different the next year. And then he did a PhD with me afterwards, right? So, and he said I wanted to try something different in that 5th year, and that was a useful thing to do, right? Because he enjoyed it, but then he came back and worked with me again. And so you can do that. You get if you're doing a master's, you get 2 research projects you can look at. So you can start thinking even then. You don't have to be too sort of rigid about it, but you can think, okay, what am I interested in theory, or am I interested in computer modeling, or interested in data analysis, or whatever it is. And you can always try both if you want to. You say, well, I'm not so sure, I'll try this one and see how it goes. And so the research projects in your undergraduate give you some ability to probe different things and see what it is you like, and then go from there. So I think that's worth. So even then, you're not really planning something, but you are kind of thinking about, what sort of project do I think I might like, and hence I will try to do a project in that area. It's not a bad thing to do, and it's quite useful to give yourself some idea of what sort of things you enjoy doing.
Yeah, that's absolutely great advice to kind of, especially as an undergraduate, maybe just start thinking about what you might enjoy, and then kind of try it out.
Exactly,
As your research project.
That's right,
yeah. So the final question that I have for you is an inspirational book/article.
Oh, dear.
I mean, for listeners, before this podcast kind of started recording, we were discussing it. And so have you been able to think
I still haven't come up with a good one that I can think of. What have I found inspirational? There must be something out there, because I can't have done this all by myself. But I can't, nothing is springing to mind. And now that you've mentioned Hitchhiker's Guide to the Galaxy, that's the only one that I can think of, which is probably I can't choose that one as well as somebody else. I don't know. I read a lot of sort of sciencey type stuff when I was, an undergraduate and things like that. And I think I had sort of this interest in sort of slightly esoteric physics, which I never quite really went into more standard physics. But, I enjoyed reading the sort of popular science books at the time, but I can't think of one that really sort of absolutely resonated with me, probably because I've just got a lousy memory. So I'm not helping you very much, I'm afraid.
No, it's absolutely fine. I mean, popular science books, there's so many out there nowadays.
There are.
Literally go to a bookstore pick one up, and I've read quite a few that have maybe decided whether I enjoy the subject or not as well, and maybe branch out into different areas of physics.
Yes, exactly.
No, popular science books is still a brilliant suggestion. Thank you for coming on the podcast, and thank you for giving us your time today.
Thank you for having me. It's very, very, very enjoyable.
So thank you for listening to this week's episode of Delving into Academics, and I hope you found it interesting. Please like, review, comment and subscribe wherever you're listening to this. And if you want to find out more about the researcher, I will have their university website page linked in the description. See you in 2 weeks for another